Hello, my name is Matt Wilchek, and I am a CS PhD student. For my paper presentation, the title is called Poltergeist, which is the Acoustic Adversarial Machine Learning Against Cameras and Computer Vision, and it was published in IEEE's Symposium on Security and Privacy. So I'm going to talk a little bit about the background to understand the technology and what the cyber attacks are on AI software. I'll talk a little bit more about the introduction of the paper, going into the threat model and attack design that was proposed, and then how the authors evaluated it in a simulation in the real world, finally concluding with some summarizing remarks and then a kind of pros and cons analysis of my own opinion about what I thought for the paper. So artificial intelligence is being used everywhere now, from robotics, automobiles, mobile devices, common appliances, business analytics across industries, and the list grows. AI allows computers and machines to learn to predict something by learning related data over time. But something not often discussed are the evolving exploits often left ignored by AI engineers across all of these fields. So enters the field of adversarial machine learning, or AML. Now, the National Institute of Standards and Technology, or NIST, defines AML as a process of extracting information about the behavior and characteristics of a machine learning system and/or learning on how to manipulate the inputs into a machine learning system in order to obtain a preferred outcome. Now, in academia, there are actually three types of AML attacks that are often focused on how to identify in machine learning systems, or how to defend against these three primary types of attacks. The first is called poisoning attacks, and here an attacker will change existing data or introduce incorrectly labeled data, and the model trained on this data will then make incorrect predictions on correctly labeled data. So for an example, an attacker could relabel fraud cases as not fraud. And then the attacker could do this for only specific fraud cases, so when they attempt to commit actual fraud in the same way, the system will not reject them. For some systems, models are continuously retrained. So for example, in reinforcement learning models, they may be trained on new data once a day, a week, or even immediately as new data is introduced, but ultimately there is more opportunity for poisoning attacks in this type of environment. The second are evasion attacks. Evasion attacks focus on the model itself. They involve modifying data so it seems legitimate but leads to an incorrect prediction. So to be clear, the attacker modifies data used by a model to make predictions and not the data used to train the models. So these types of attacks are more associated with fields like image recognition. Attackers can create images that look perfectly normal to a human but results in completely incorrect predictions. And then the third is called model stealing. Model stealing attacks focus on the actual model file after it has been trained. Specifically, an attacker wants to learn about the structure, the architecture, how many neural net layers were used, how many neurons are in it, the activation functions, like the actual nitty-gritty of how a model was made, or the data used to train the model. So for example, an attacker could identify exactly what words a spam filtering model will flag. And the attacker could then alter the spam phishing emails to ensure they are delivered to an inbox. So my paper review on Poltergeist, Acoustic Adversarial Machine Learning Against Cameras and Computer Vision, introduces a new evasion attack that can severely impact autonomous driving vehicles or vehicles that use some type of object detection systems, maybe like Teslas or something. So, for the introduction, autonomous vehicles depend on computer vision-based object detection algorithms to automatically classify objects when cameras capture road images. So, correct classification in the midst of a dedicated adversary is important to ensure safe driving decisions. Since the quality of captured images is absolutely critical to robust object detection, modern cameras not only consist of an image sensor, but also an image stabilizer designed to de-blur the images by compensating the jitters of the cameras while they're in motion. The added feature, i.e. image stabilization, improves the image quality in small scenarios, yet could be exploited by dedicated adversaries. So for example, in figure 2 that was in the paper presented, we can see a car captures an image with a traffic light in it. When the image is captured, the car is in motion and the image is blurry. It's passed to an inertial sensor to stabilize it, which results in a clear image passed to the object detection algorithm. Finally, the actual model and algorithm results in the correct classification that, hey, it's a traffic light. So this paper identifies a new system-level vulnerability resulting from the combination of the emergent image stabilization hardware susceptible to acoustic manipulation and the object detection algorithms. So the authors propose a new evasion attack to exploit these vulnerabilities and call them Poltergeist attacks, or PG attacks. So PG attacks can be initiated by controlling the inertial sensors of the stabilizer via a resonant acoustic signal, which creates blurred images because of unnecessary stabilization, and then finally results in the entire misclassification of the image, as shown in figure 1. The authors try to quantify the impact of acoustic attacks on the level and patterns of the image blur, regardless of the type of cameras, but they try to find an example of an effective blurred image that will lead to a successful misclassification using common academic object detection models, such as YOLO v3, v4, v5, FASTA, RCNN, and Apollo. These are all very standard object detection models in the computer vision field. And in one of these pictures, you can see actually some of the new AI software that the Dodge Ram Revolution is going to be, coming out potentially, and they're tracking, movable objects through the windshield, which is pretty amazing. But it just shows how the evolution of object detection is being used in driving. So for the threat model, the authors of this paper evaluate 3 different types of methods creating a PG attack. The first is called hiding attacks, where the goal of the adversary is to let the object detector fail to identify an object. I'm timing myself. Fail to identify an object that is of interest to the systems. The second is called creating attacks, where the adversary blurs the images such that the object detector detects a non-existing object as if it were physically present. And then the third is called altering attacks, where the adversary blurs the image such that an object is entirely misclassified to another object. So for an adversary to carry out any of these attacks, they would have the authors assume that the attacker would have certain assumptions in order to perform this. One is called black box object detector. So the adversary has no prior knowledge of the object detection algorithm, but not limited to its architecture, parameters, etc. However, the adversary can obtain the classification results and their confidence scores for each detected object, which are default outputs for various object detectors like the YOLO v3 or FASTA RCNN. Anyone can look up this information online as public knowledge. Second, a camera and sensor awareness, where the adversary can acquire and analyze a camera of the same model as the one used in the targeted system, for which they can learn the information about camera parameters like the focal length, exposure time, parameters of the inertial sensors, information about the physical hardware that could be on the cars. Again, could be public knowledge. When someone knows what kind of cameras and systems that Tesla is using, they can easily Google it and find the specs for it. Third, acoustic attacking capabilities. So this is the device that's actually doing the acoustic injection, where the adversary can launch an acoustic injection attack toward the inertial sensors in the targeted system. An acoustic injection could be accomplished through setting up a speaker or an ultrasonic transducer array along a roadside, attaching speakers to the surface of a targeted system, or controlling a compromised onboard speaker in the targeted system like a Bluetooth music speaker in the car. But potentially large noises, kind of like some of the silly examples, some of these, unsuspecting people could potentially be the attackers. They could be projecting the acoustic injection from these speakers, while they're walking around, playing music. Who knows that maybe some of these sounds match the specific pattern that is used to blur, images for, computer vision software in cars. All could be possible. So for the attack design, on how the attack is made, going a little bit more into the nitty-gritty, like I mentioned, to observe intentional attack results, the authors first simulated model attacks to achieve the 3 threat models. The authors walked through in the paper how they overcome 2 primary challenges. The first was how to quantify the impact of acoustic manipulation upon the parameters and levels of image blur. And the second was how to optimize the blur patterns for an effective and efficient attack against black box object detectors. So finding solutions to these outcomes led to the development of 3 modules to control the acoustic injection. The first is called blur pattern modeling, and in this module the authors modeled different patterns of blurring at different angles to the camera while it was in motion. So for example, a linear motion blur is the blur pattern caused by linear pixel motions, which is shown in figure 13a. Radial motion blur is the blur pattern caused by radial pixel motions along rays towards or away from the image center, and that's shown in figure 13b. Rotational motion blur is the blur pattern caused by a rotational pixel motions along an arc, and that's shown in figure 13c. And then something called heterogeneous motion blur, which is kind of like a combination of the first 3, but simultaneously occurring along multiple different angles to the camera, resulting in a heterogeneous blur pattern as shown in figure 13d. So the second module is called attack parameter optimization. And in this module, the authors adjust each of the blurring patterns to an output of the 3 types of evasion attacks that I mentioned: hiding, creating, altering. For example, in the case of hiding attacks, to hide the prediction of a particular object of interest, the products of the blurring of the camera motion should be less than the threshold that determines whether the object can be detected. And so the authors designed something called an objective function, which is actually a mathematical formula that is incorporated to create these adversarial machine learning models that can help create these preferred outcomes when the ejection is made. So they are using machine learning to attack another machine learning software. And part of the software that these adversaries could make can be complex. And so in the world of AI and machine learning, when it comes to training algorithms, they, especially neural networks and machine learning, they require these mathematical advanced functions called objective functions to help fine-tune and train these models. And so the authors, in order to create these 3 different attacks, they ended up creating 3 objective functions that were used. And so in the presentation, I'm showing an example of the hiding attack one. And so the magnitude of that represents the attack cost that should be minimized to ease the burden of acoustic injection attacks. The objective function shown on the slide is the formula used to create the hiding attack, right? So W1 and W2, they can be seen. I got right here and right here. They're used to represent the trained weights in the AML model to balance the attack success rate and cost. And then the equations below here, sigma 1 and sigma 2, I think they're sigmas, they might be something else. Those are two different equations in the bottom right, and they represent a physical attack capability restrictions that point to the accelerometer and the gyroscopes of the actual physical hardware. And so the objective functions are made similar to output a creating attack or the altering attack. They have their own unique ones in the paper for the other two. But the third module is the actual injection of the crafted acoustic signal. So to adjust a device used to output a very biased signal to create that output that is desired, first finding the acoustic resonant frequency of the target sensor by frequency sweep is done, and then the authors stabilize fluctuating false outputs into constant outputs by shifting a acoustic resonant frequency to induce a direct current. And so what all of that essentially means is the authors actually can control the frequency and strength and wave of the sound that is going to be emitted on by like a speaker on the cameras, which will create so much destabilization that it will actually create a particular pattern of blurring on incoming images to create this output. So then the desired output signal is then created by modulating on top of the acoustic resonant frequency crafted by the right blurring and optimization, which is what I just said. So how they evaluated it, first they did a simulated environment. The authors considered two sets of evaluations in the paper. The simulated one where adversarial blurry images are generated by the blur model with public autonomous driving image data sets as input, and then they go on and do the real world evaluation. And in both evaluations, blurry images are fed into the CNN algorithm for object detection. The classes detected in the evaluation tests were either person, cars, trucks, buses, traffic lights, or a stop sign. So the first data set they used to help evaluate for simulations was called a BDD100K, and apparently is considered as one of the largest and most diverse open driving data sets, which covers different scenes, weather conditions, and times of day. The second is called Kitty. Is another widely used data set in mobile robotics and autonomous driving research, which captures real-world traffic situations with many static and dynamic objects in diverse scenarios. But for both data sets, the authors only sampled 200 images that were randomly selected for the evaluation. The attack success rate, or SR, is used as a primary evaluation metric, which is the ratio of the number of successful attacks against an object detector over the total number of conducted attacks. So for the simulation evaluation, hiding attacks they found can achieve an overall success rate of 100%. That's really, really huge. I mean, that's crazy. Scenario-targeted creating attacks can achieve an overall success rate of 87.9%, and then they found that the altering attacks can achieve an overall success rate of 95.1% against all four academic object detectors: YOLO V3, V4, V5, Faster RCNN, and Apollo, which was a commercial object detector. But the performance variations between all these detectors in the table shown are caused from varying results in detecting smaller objects that were in the pictures. And Apollo doesn't actually support the detection of traffic lights and stop signs. So there's some variation between the models, but the success rate of the attacks is massive. The authors go into a significantly more detailed table and description of these results, and they're presented in the paper, breaking down the results by each of the classes of detections for each model. I'm just showing a very short summary. For the real-world attack evaluation, this was interesting. For the real-world evaluation, the authors implemented the PG attacks towards a Samsung S20 smartphone mounted on an Audi Q3 car that served as its computer vision. The target smartphone uses an accelerometer and a gyroscope for motion feedback. The PG attacks are carried from inside the car on the smartphone and are derived from an arbitrary waveform generator, which is for acoustic signal generation. And they also had a Fostex Horn Super Tweeter speaker for acoustic signal beaming, and then an audio amplifier used before the speaker for increasing the volume of the ultrasound. And then they had an uninterrupted power supply used as the main power source for all these things, and a DC power supply used as the power source for the audio amplifier. And these can be shown in Figure A that the paper presented. The speaker is placed towards the targeted smartphone at around 10 centimeters and a power of 8 to 10 watts to actually launch the PG attacks. The authors drive around a city lane, city crossroad, tunnel, and campus road in each attack, and they first take a clear image of the scene and generate and optimize attack parameters with the remote server. Then they induce the desired sensor outputs by emitting the acoustic signals derived by the optimized attack parameters. And once the acoustic signal became stable, they recorded the results. And in Table 4, they actually shown here some of the results of that real-world evaluation. The average success rate for the hiding attacks was still 98.3%, extremely high. Creation attacks and altering attacks were only around 43%, which was a significant difference in the actual real world. So for a little bit of the conclusion, the authors do demonstrate PG attacks can exploit vulnerabilities of these inertial sensors embedded in image stabilization systems. They can also mislead the object detection algorithms to ultimately affect the decisions of these systems like autonomous vehicles. The authors also conclude some potential defense mechanisms to protect these PG attacks. The first is called MEMS inertial sensor safeguarding, which is like surrounding the physical sensor with like a special fabric and that could protect it from injection. In addition, you could use a microphone that maybe could be used to detect the injection attacks, and it could alert the systems to be like, hey, shut down. We're noticing, unstableness, anomalies. Another is with an image stabilization technique, and so you can by adding like additional digital image stabilization that could de-blur the images with pixel information only after the existing one. This could serve maybe as a second barrier to blur the images and thus the attacks. And they have object detection algorithms, so you could maybe remove adversarial blur patterns through a guided denoiser to protect the object detection algorithm. In this way, it's possible a denoiser might mitigate the threats, but could affect the detection efficiency and accuracy of the algorithm. Another method could be actually to improve the model, but that risks on making it not as generalizable. And then the last is something called sensor fusion techniques, and especially in autonomous vehicles, they use a lot more different sensors like LiDAR imagery or GNSS. And using a combination of all these different sensors for a successful attack to occur, the adversary would have to target all these sensors simultaneously, which would be very much more difficult. So going right into the pros and cons to kind of summarize, at me as a reader, I think these are kind of like my points. I believe that the paper presented was very novel in AML. The authors discover new vulnerabilities in the hardware used for AI computer vision, and they present their findings with a very thorough evaluations and simulated in real-world environments. However, for the cons, during the real-world evaluations, the hardware used was limited. They only used a Samsung smartphone as a primary camera, which could vary the image quality, processor, the algorithm. In addition, there could be additional different kinds of speakers or audio amplifiers that I think could change the effectiveness of the ejection attack. Therefore, I think additional comparisons of different hardware used would strengthen the paper. The authors also have a small limitation section and cite that they did not attempt continuous injection attacks, and I agree that only presenting a single attack injection using these PG methods is a strong prototype of the concept, but not to be an effective to be more effective. More research is definitely needed for continuous attacks for this method. And then lastly, the authors only discuss a very limited research in the related work section. I think some of the concepts sound similar to what they propose, and I think it would be very interesting to see differences in how the similar attacks affect the AI algorithms or hardware for similar purposes. And that's it. Thank you very much.